Swayam Prabha. Digital India. Educated India.
Accordingly, we showed that the angular velocity omega should be V naught by R. So similarly, we do it here, but there is just one small additional component is here. What is that all about? So a similar approach we apply here. For example, if you want to get the acceleration of A is acceleration of A with C, I'm sorry, A with C here, the normal component and a tangential component. Okay, without going too much into the algebraic equations and so on. So now that we understand how to do it, so acceleration of C is, let us say, A naught. So I'm putting the magnitude and there's a direction. And acceleration of A with C, I'm sorry, yeah, A with C, the normal component. So A is rotating about C. So we know that the normal component is R omega squared. And then it is directed from A to C. I'll show the direction here. Okay. So this is this one. And tangential thing is again a relative component. So with alpha, if it is rotating about C, so the acceleration, the tangential acceleration of A will be R alpha and going to the left. Okay, so this is how we can show a vector equation. So I'm showing the magnitude and the direction. This is as good as your IJK, and in fact, this is even faster. So we'll collect the terms here. Okay, so that means that this acceleration of A, there's one component in the horizontal direction and another component in the vertical direction. So this here, this point A, and if you look at A prime, so this is the tangential, horizontal component of acceleration of A. So since these 2 points are in contact and it is rolling without slip, so just like we said that the relative velocity here between A and A prime in the horizontal direction, because that's where the slip might take place, was 0 for velocity, and as well as the same thing for this is the acceleration, tangential acceleration component, or we can say that horizontal acceleration component of A. So this, but however, we don't have any issue with R omega square because this is anyway, so that's in the normal direction. So if it wants to leave, so we have no objection to that. But however, only the horizontal acceleration component of A should be same as A prime, and that should be 0 here. Okay, so that should be 0, and because there is no slip, which means that this is going to be 0, and this is the relationship. So A naught is R alpha. So this A naught and this alpha are not independent, and they have to be related by this relationship. Okay, very simple, but the emphasis of this one is our complete analysis. So that still leaves. So if you do that, so that means that A, acceleration of A is left with R omega square. So that means that this point A is going to have a vertical acceleration, and obviously you can see that. So if it has, so you can see that this point A, as it moves, obviously it is going up and up. So similarly, though its velocity is 0, it is going to pick up velocity in the vertical direction. Okay. So at this point, it's the moment it comes here, so it's going to have certain upward velocity component. So that is because of this acceleration component. Okay. So like this, so once you have this, so that means that this acceleration component is like this, or omega square here. And what about any other point? Now that you are quite conversant and quite expert in all these things. So for example, this point here, this is point D. So it has, so acceleration of C, right? And so acceleration of D, if you want to write here, if you want to write acceleration of D, is nothing but acceleration of C plus D with C, the normal component, and D with C, the tangential component. So we can definitely see that it's nothing but a horizontal component like this one. So this is R omega square, and this is directed like this. And one more component, so this is R alpha, it is in this direction, so upward direction. So like this, so here obviously you have A naught or omega square. Interestingly, now this has come in the same direction as this, so it doesn't matter. And then there is an R alpha, now it is in the vertical direction. So all these things put together, that will give you the total acceleration of D. So every point has certain accelerations, 3 components, and similarly here. And so here we have a normal acceleration, an acceleration A naught, and on which you add on the tangential acceleration. So like this, so we can do the complete analysis of the acceleration of any point. We can come up with. So only thing which you have to understand here, velocity of A is completely 0, whereas acceleration of A is not completely 0. Acceleration of A in the tangential direction is 0, but however it has a normal component, it's not 0. So like this, so we can, this is a very important analysis, very simple looks, but it has a lot of implications. You have to understand it completely. So we'll continue this one. So I want to give you a small trick here, interesting tricks, which will be helpful in your analysis. So we have been doing this. I started this one yesterday. So this is the, say, body 1. So given omega 1, for example, so if you want to find out the velocity of C and the omega 2, so 2 components you can always find out. Okay, so let's do this analysis. Is a crank of length R and a connecting rod of length L. So this we can connect A and B. So velocity of A is 0. So this is the velocity analysis, and velocity of B we can find out as omega 1 K cross R A. So this is how you can write it if you want. And this is at this particular instant if it has cos theta here. So you can do this. This is fine. Okay. Or on the other hand, we can also very easily say that velocity of B is R omega 1, and so it's perpendicular to this like this one, and so we can say I can either write it in terms of ij like this, or simply I can show the magnitude and show the direction. So with the vertical, it makes an angle of theta. Okay. So in fact, you can even write this into horizontal and vertical components. That's also is equally good enough. So you know the velocity of B. Now we want to apply the velocity of C with respect to B so that we can relate it to velocity of C. So velocity of C with respect to B is, again, in a simple sense, you can also write it like this, or I will write it simply as L omega 2, and if this is phi, so if you think it's a counterclockwise, right? So that means that here this is rotating like this, and so it will go like this, and yeah. So either you represent it this manner or write it in this manner, both are equally good enough. So then finally, what is the velocity of C then? So the velocity of C is known to be a velocity of C in the horizontal direction. So all these things we can put them together as.
Sir, in expression for VB, it should be minus omega 1 k cap, right?
Minus omega 1.
Sir, in first line.
Oh, here. B with respect to A, omega 1 k. So this, oh, sorry. Yeah, you're right. So I'm putting it clockwise here. So you should put a negative, right? Otherwise, this is true for a counterclockwise rotation. You're right. So you can continue this one. But this is right? So because r omega 1 is the magnitude and it's in an angle of theta direction with the vertical. So we see B. Okay. So this is now I can write it in this vector representation, and I have r omega 1 and L omega 2 . Of course, you know how to solve for phi. Yesterday I told you it is nothing but the vertical component here should be same either you consider from this side or from this side, and that is r sine theta. Here r sine theta is L sine phi. You can do it. So this is a vectorial representation, and you can write here into horizontal component and vertical component. You can do that. So for example, the horizontal equation will look like this. This I think I wrote yesterday. So using this, okay, so this is using this, you can write down the equation. Okay. So interestingly, we can, okay, I'll come to that. Maybe I'll come to it. So let me finish up the acceleration analysis. You can solve for omega 2 and the velocity of C. So two equations, two unknowns you can solve. So the acceleration analysis, if you want to do, so exactly it goes in the same line, but now we'll get one more component. So acceleration of C is acceleration of B with C with so acceleration of B can be found out from the link AB, which is first link. And so this is, if you, it may have alpha here, or alpha 1 may be there, or maybe 0. So if your alpha 1 is 0, so then we can say this is what R omega squared, and this is at an angle of theta directed from B to A. So I can show it like that. And C with B, the normal component, I can write it as L omega 2 squared, and this is directed from C to B, right? Right, we can write it like that. And one more thing, ACB is L alpha, and then this is more or less in the same direction as this. Okay, so this is in a nutshell, very clean and neat, that each is represented by magnitude and the direction and L omega 2. So this obviously you can very easily, you can put it in the horizontal component equation and vertical component equation. Okay, and you can solve for what are the two unknowns here. So the two unknowns are the well, this is now also can be put as, we know about acceleration of C. So it has a magnitude and the direction is horizontal. So you can solve for AC and what else? So alpha. So this alpha 2, let me put it as alpha 2. So you can solve, you can make an equation in horizontal component and a vertical component, you can solve for it. And it will be interesting to draw the acceleration diagram always. So here, what is that which we have? This is acceleration of B, which is given like this at an angle of theta, right? And then we have this one at an angle of phi, a slight angle. So this is C with B normal, and then we have C with B tangential, and finally this should be in the horizontal, adding all three components, B and C with B normal, C with B tangential. So you should end up on the horizontal line again, because acceleration of C is horizontal. So this is either this way, or in the component form, it is all same. Okay, I want you to be well versed with all the approaches. You can draw this here, right? And you can resolve it in the horizontal direction, right, or vertical direction, and make the equation even by looking at this one. Okay, so like this, so we can solve, and I can give you a numerical example, but I don't think I have the time. Another thing here is that if it sounds useful for you, sometimes it's a quick 2-minute thing, is that So this is a vector in the XY plane, and you may have many of them. And usually what we are getting here is a sum of these. For example, maybe R1 is, you will have these equations, right? Sometimes. So how do you solve? Some of them you have to solve for magnitudes. So interestingly, if you can represent it, you can represent it like X and Y components. Okay. Something like this, or we can even put it in the polar form, right? So either X components or in the polar form R theta. So these are equal to each other. You know that R is X square plus AY square under root, theta is tan inverse AY by X. So and similarly, AX is R cos theta, AY is R sin theta. So you can, these are equivalent. So this equation now, if I write it in polar form, interestingly, so each is represented quickly. So this is in the polar form, this is the Cartesian form, right? So each is a vector. So this shows this is a vector, this is a vector, this is a vector, and you cannot really add them unless it's in the component form, unless it comes in the component like this one. Only when you have write it in XY components, then only you can add. Otherwise, this is the vectorial form. Okay. So interestingly, if you want to make a component equation, so you have to write R1 cos theta 1 is equal to R2 cos theta 2, R3 cos theta 3, and similarly R1 sin theta 1 is equal to. So interestingly, if I change the axis here, very interestingly, if I change this, we will discuss, but I just want to, if I change it by transforming slightly into another coordinate system x prime y prime, so what will this be? Okay, what will this be? So this will, what happens is that the magnitude will not change, but however the angles will change. So this now angles have changed to theta 1 prime, theta 2 prime, theta 3 prime. So what is the advantage of this one? Is it possible for you to choose a theta 3, for example, to be 0? So that means that if you, from this, you can, so theta 1 prime will become theta 1 minus psi. On the other hand, I could have arbitrarily subtracted anything. So for example, if I subtract theta 3 from all of these things, so it looks like theta 1 minus theta 3, theta 2 minus theta 3, and this will become 0. What is the advantage of this one? So now if you want to make an equation here in the y prime direction, if you want to make an equation in the y prime direction, so what will happen? R1 sin theta 1 minus theta 3 is equal to R2 sin theta 2 minus theta 3 plus R3 sin 0. So that component will become, the contribution of this one will become 0. So if you can, that way, if you can make this angle 0, so its contribution will be 0, and then straight away you can say that R1 sin theta 1 minus theta 3 is equal to R2 sin theta 2 minus theta 3 by eliminating this one. Okay, we'll discuss this in the next class, but this is just a trick how to avoid solving those simultaneous equations in the vectorial. Okay, I'll stop here.